and thanks for everyone joining today. Today I'm going to talk about the status of OpenFabric OFI support in MPICH library, what we have been doing with Fabric, and what's on our plan and the upcoming MPICH release. Next slide, please. So first of all, I want to talk about what is MPICH and then why we choose OFI, and then next we're going to see some of the details of features that we leverage from using Libfabric and what we have planned, especially for the new collective framework and GPU support, which is directly targets all the future exascale machines. Next, please. As you may or may not already know, MPICH is a high-performance MPI library that is open source and it's portable, and we have the library has been mainly developed by Argonne, and with the collaboration with many vendor partners, including Intel, including Cray and Mellanox, and this is so the latest version we have is 3.3.2, but what we're currently working on is 3.4 series, which is supposed to come out this summer. And if you're interested, this is our website where you can find more information about the library. Next, please. So our philosophy with MPICH is instead of having this library and whichever one you use, and what we choose is what we call a MPICH ecosystem model that we're trying to create here. Basically, we have the open source MPICH library at the center, and we have a lot of these vendors library that is that use our open source code, but apply their specific optimizations for their hardware. Right? The philosophy is basically what we're trying to do as MPICH is we're trying to provide general optimization for MPICH, for MPI communication. But vendors who have better knowledge of their hardware and their clients' needs, they would come into and say, we want to further optimize in this direction for our hardware or client. And outside of that, we also have a close collaboration with the application team and you see here this scientific library teams. We all have this is essentially become a big MPICH family. So next, please. So we have been in the MPICH library we've been using OFI for quite a long time, and the main reason that we decide to adopt Libfabric is basically it is allow us to support a diverse range of different hardware through a common API. So as a library, we don't have to go in and implement all the low-level support for different hardware. That is being taken care of by Libfabric, which is getting constantly updated, and it's also because the Libfabric interface has a close abstraction of MPI, so it's much easier to for us to implement a full functional library on top of that, and plus it has strong vendor support from our vendor partners, so it's a fairly simple choice for us to base our development on. Next one, please. So the biggest changes from in the past, well, in the current stable release through 3.3 series is the introduction of what we call CH4 device. So so in MPICH we have inside MPICH we have what we call the abstract device layer, which has the implementation of the functionality that interfaces from the upper level MPI interface to the Libfabric and low level network interfaces, and we provide, and all this implementation is provided by the device abstraction layer. And the CH4 is a completely new device that we designed to use Libfabric and also other network libraries. And what we're trying to achieve here is a very low overhead communication, and also have a better support for highly threaded environments, and also for multiple network endpoints. Next, please. So this is an overview of the present day MPICH architecture. First, on top of that, we have this MPI layer, which provides the interface that what MPI standard specifies. And we have the collective support, we have the data type and all that stuff. And all the heavy lifting is happening below this abstract device interface. This CH4 device. We have a CH4 core that handles some of our architecture specific collectives, and we have active message fallback and GPU support. And these fallbacks are only for the cases of forward functionality that the network are not supporting. So basically, if anything that the netmods, which using Libfabric or USENIX have natively support, and we'll be calling them directly instead of going to the fallbacks. Only in the case where some mod functionality is not provided by the network library, then we'll go to the fallback route. And in the case with Libfabric, we have a specific capability sets based on what provider is being used in Libfabric. Say so if you have a PSM2 provider, then we know that these certain functionality is supported by hardware. Then in that case, we'll be using the native functionality provided by OFI. So that's overall. And beside the NAC mod, we also have a SHMEM mods that support shared memory communication. So currently we have POSIX implementation, and we also have XPMEM support in shared memory communications. Next slide, please. So one of the main goal of having this of designing this CH4 device is we want to have a very lightweight communication. The rationale behind this is because the network hardware is become more and more capable, being able to do hardware tag matching and to do a lot of heavy lifting in the MPI communications. Especially with Libfabric, what the MPI library actually needs is taking this communication information like buffer, data type, and all this information and just give it to Libfabric. So that's why we're trying to introduce a very lightweight library on top of Libfabric, and which basically reduces the instruction counts and memory usage, and try to use as much as possible, as much possible native functionality from the fabric. And we even try to do one step further by inlining the Libfabric functionality into the MPICH library itself. So essentially mitigating all the function call overhead in the software stack. So if you look at the figures on the right, this is some early number when we run CH4 with the BG2 machines that we had at Argonne. So essentially, this is using the lamps, and you can see using CH4 has a significant performance improvement over the red part here, which is the MPICH with the CH3 device. Next slide, please. And besides the library communication, another big improvement we're trying to be included in the MPICH here is what we call the multi-virtual network interface, the multi-VNI. So what the idea here is to use this multi-VNI infrastructure to improve the performance of multi-threaded communication. So what we provide here is inside MPICH we have this terminal virtual network interface, which can be mapped to different hardware contexts or scalable endpoint Libfabric, and within each VNI the traffic are serialized, but in between all these VNI they're running parallelly, and because there's no shared resource between them, so instead of having a global lock, we'll be able to do a per VNI locking, which is much less contention in multi-threading. And what the user need in this case is trying to expose they need to expose the thread parallelism at the threading level through the library. So one common case is you can have different threads using different communicator, and inside MPICH we'll be able to map different communicator to different VNIs so that their traffic getting separate. And by the way, I want to point out this is the VNI is not visible to user, so this is different from the endpoint also at the MPI forum. So with the VNI, we don't actually need the endpoint proposal, because all the user need to do is trying to use different communicator or different tags, and we can do this mapping internally, so it's not exposed to user. Next, please. And also with this is some of the performance numbers with the MPI+THREAD using the VNI. So as I mentioned, the user doesn't need to know about the endpoint. It's still one endpoint, but if the thread are using different communicator for messaging, then if you look at the figure on the right hand side here, we'll be able to get a performance that is close to MPI single threaded, which is the blue line here. So if you look at the blue and green line, these are the single threaded version and the multi-threaded version with separate communicators. As you can see, the performance are very close. And the red line here is basically using multi-threaded communication with the MPI component. So in this case, we won't be able to optimize anything, because from the MPI perspective, from the MPICH perspective, it seems all the traffic is coming from the same pipe. So it only gets to map to one VNI, and essentially this is the baseline that we have today without any optimization. Okay. So next slide, please. So next, I'm going to talk about what we have been working recently for our 3.4 implementation, and how that is related to the Libfabric work and some of the vendors' collaboration work. Yeah. The first part I want to talk about is what we call the new collective framework. What we're trying to do here is trying to provide different implementation of collective algorithms that is optimized for different use cases, like for the communicator size or for the network topology, or in order to support the hardware acceleration. And we have a way for the user to choose what is the best algorithm at the moment based on the communication parameters that is given to the MPICH. And next, the second part is the GPU support. So because all the future machines are going to have GPUs, so this is a big push from our side to make MPICH to support GPU. A lot of this native support is actually come from Libfabric, so we're relying on native support from Libfabric in that sense. But what we're trying to provide is a fallback path for the case where, for example, non-contiguous that is which is not supported by GPU natively. Then we have a fallback path to efficiently support that function. Next, please. So the first is the new collective framework. This has been a significant contribution from Intel. Basically, they write out this whole system of a template-like structure that's allowed easy expansion of collective algorithm, and they have contributed many algorithms for the existing collectives. So so this has been merged in MPICH for a while, and basically, if we roughly count, you can put the algorithm into three categories. One is for hardware acceleration through the OFI, and which is using the collective interface that the OFI is providing. And then we have a more general algorithm that optimizes for that uses for point-to-point communications. Next slide, please. So to effectively use all these collective algorithms, one big improvement that Intel is contributing is the collective selection framework. So what the framework does is it allows user to choose different collective algorithms based on multiple criteria, including communicator size, the message size, and all that stuff. But more importantly is this, it provides a way for user to say, I know that my application has this certain communication patterns, and I want to run on this specific machine. And what is the optimal algorithm for specific communication? The user don't have to guess. The user can actually use some external tools to do some profiling runs on the machines and come up with the parameters that guide the decision. And all this can be generated into a JSON file, which in turn is parsed by MPICH at initialize time. So then after MPI init, then it will have an internal decision tree for choosing algorithm. And then at runtime, it can make these decisions on the fly. Okay, so next slide, please. Okay, so that's for the collectives. The plan for the GPU is relatively simple. So most of the internal GPU support, especially the native GPU support, we rely on the network library, in this case, Libfabric, and also USENIX. And what we're trying to provide here for internal is a fallback path for the case where native GPU is not supported. For example, if I have a non-contiguous native buffer, then we have to pack it first, and then utilize the native path to transmit it. But in that implementation, we have also to consider what kind of buffer that we're packing into, and where is the data is coming from. Trying to reduce the data copy by using GPU register buffer or network register buffer, in essence. And on the intranode side, what we implement is the GPU path using in the shared memory model, in public shared memory. And what it will do is it will try to support the interprocessor, try to use the native IPC interface if possible, and otherwise it will fall back to just transmitting the GPU buffer information inside the shared memory communication part. So a big part of the support is the data type engine, which I'll mention in the next few slides. So this is basically the overall plan of GPU support in MPICH. Next slide, please. So currently, a lot of these support focus on getting the non-contiguous data ready and being able to use GPU. And what we did is this YAXA library called the YAXA data type engine, which is available as a separate project on our GitHub. But it is also embedded as a submodule in MPICH source code, so you don't need to manually check those out. Use MPICH. It supports all different types of the data packing and unpacking, and what it has is it has a data type front end that interfacing with MPI data types, and for each of the different hardware, we have a backend for packing and unpacking to and from those hardwares. So currently we have a CUDA backend for GPU support, and now Intel is working on the backend for their GPUs at the moment. So what the backend provides is not only the capability to access the GPU buffer in the data type engine. It also provides a set of GPU kernels for packing using the GPU. Okay, so the packing can actually happen and drive on the GPU side. So if you look at on the right hand side, if you compare it to the host, this is just a comparison of the performance of using GPU to drive packing versus using a CPU. So this is the current state of the GPU support on the non-contiguous data. And by the way, this has been already been merged in MPICH. So if you check on master, this is already there. Next slide, please. And so that's roughly that is the major function feature that we're going to introduce in MPICH 3.4. So the GA release is going to come out in this summer. So right now the multi-VNI and collectives are already merged in there. The only big piece that we that is still need some work is the GPU support, but we should be able to make the release on time. So I think that's all the slides I have, and go to next. I think it's Thanks everyone. If I can take questions. No?
Thank you, Yanfei. Give it a minute, see if any questions come in, I guess.
Okay.
Let's see. Okay, I guess no questions for you today, but I will put you in touch with anyone who reaches out, okay?
Sure, yeah. And thanks everyone for coming. Thank you.
Thank you, Yanfei.